Okay, so we've now kind of looked at hypothesis testing for one population, two population, and kind of this unique, it's like one population but two time periods, or one county but two different groups within the county, so that match pairs. Now we're going to think about, well, what if we don't just want to look at means and proportions, right? Can we do hypothesis testing for any other statistic? And the answer is yes. So, what are some other statistics we have maybe talked about in the past? Well, we had these correlation coefficients, and kind of that came from our covariance. So what we can do is look at that correlation coefficient, and we can actually do a hypothesis test for that correlation coefficient. Okay? And what that correlation coefficient was the relationship between variables. Remember, because we took the covariance divided by the sample, or sorry, sample standard deviations, it kind of made it unitless, and it gave us a kind of put it within the range of 1 to -1. Right? The closer to 1, the stronger the positive relationship. The closer to -1, the stronger the negative relationship. So we want to look at this correlation coefficient, but we can actually do better than that. Right? We can do better than looking at that correlation coefficient. We can look at something called a coefficient, right, from a regression or linear regression. So the idea of regression, I say it's a review here. I probably shouldn't have reviewing. I should just say kind of linear regression maybe should be the title of the slide. But we've got two variables, x and y. Right? We want to know how they're related. So can we use values of x to predict what y is going to be? So if x goes up, how much do we predict y goes up, down, or does it just not stay? Does it not change? Does it stay the same? So what we're going to do is we're basically just going to have this equation, y is equal to a plus b times x. Okay? That coefficient b is going to tell me if x goes up by 1 unit, how much does y go up by? Really, all this is, linear regression in its most simplistic form is really, we have a line, right? We're trying to figure out, say I've got this line, right? Here's my x, here's my y. All I'm trying to do is, what is my intercept a, and then what is the slope of the line b, right? And the slope of the line tells me if x goes up by 1 unit, the slope is how much, right? We'll call this y, where y starts. If x goes up by 1 unit, y goes up by whatever the value of the slope is. Right? So we're trying to figure out, we've got all this data, x and y. We plot all that. We draw a line that best fits the data, and then we try to figure out, okay, now that I have my line of best fit, what is that line's intercept and what is that line's slope? Right? That's really linear regression at its most simplistic kind of explanation. Okay? So we've got this equation for the relationship between y and x. If that slope is positive, right, then we know there's a positive relationship between y and x. If it's pretty much 0, there's no relationship. If it's negative, then as x goes up, y actually goes down, right? So when we look at that equation, what we're going to call the y variable is the dependent. So actually, I always use 3 terms: the left-hand side, the dependent, or the y variable. Right? The right-hand side variable x, we're going to call the independent, the right-hand side, or x variable, right? Or controls, sometimes we'll eventually get into. So we got our dependent and independent variable. And what regression analysis is, it looks at that scatter plot of data, and it figures out what the value of a for the intercept and what value of b for the slope would create a line that best fits all of that data. Right? So we had something like this, here's our line of best fit. Our intercept a is up here. It's downward sloping, so the value of b should be negative, right? As x goes up, y is going down. Okay. Here's another one. I draw a line of best fit. Looks like there's no relationship here, or that the slope would pretty much be 0. Here we've got a positive relationship, or upward sloping line, so our slope here, b, would be positive, greater than 0. And then here another one, sloping downward, b is less than 0. We won't do it in this class, but we can actually estimate, we can figure out if we had a nonlinear line. Everything we're going to do, we're going to keep linear, but we could do some nonlinearities as well if we wanted to. So I won't waste too much time on here because we're not going to really focus on how we would estimate nonlinear lines, but just so you know, it is possible. Right? So we've got kind of this value of b. Let's say, like, I haven't described, we haven't seen exactly what the output looks like yet, but let's say I use this, here we go, regression analysis to then get an estimate for what b, right, for what that slope is that would best fit the data. Now remember, it's still an estimate because I don't have population data, I just have sample data. So I'm getting a line of best fit, but for the sample that I have. So we're getting like instead of a sample mean, we're getting a sample coefficient for the relationship between x and y. So once I have that coefficient, I can do some hypothesis testing with it, right? I can say, is that coefficient greater than? And here I can do any value, but once again, what we're always going to use this assumed true value of 0, right? Is that coefficient greater than 0, less than 0, or not equal to 0? Right-tailed, left-tailed, two-tailed test, okay? So what we're always going to start out assuming is that the relationship between these two variables, x and y, is 0. If we can find enough evidence, right? Yeah, in fact, everything we're going to do, we're not even going to use a right or left-tailed test. All the examples that we're going to work with, we're always going to start out with, is this coefficient not equal to 0? Or we're assuming that it is equal to 0. So once I assume that it is equal to 0, if I find enough evidence that suggests that b is some value that is different than 0, at a high enough level, I can get a p-value that's small enough, then I can reject the null, which is I can say I reject that this relationship is 0, or I found enough evidence that supports the idea that there is a relationship between x and y. Okay? So what are the steps? It's going to be no different than what we did with other statistics. You determine the null and alternative hypothesis. Like I said, this one's easy actually because what we're always going to start out with is that for linear regression, we're always going to do this hypothesis test. So if I ask you on an exam, what is the null or alternative hypothesis for any coefficient, any type of regression output that we're looking at, it should always be that, and kind of here, I'll call it beta, but I'll just keep it what I was consistent with. I was calling it b before. So it'd always be, I'm assuming it's equal to 0, and the alternative would be that it's not equal to, right? It's always going to be our hypothesis test. So we always know what our null and alternative hypothesis is. We need to know what level of confidence we're trying to reject at, so we need to know alpha. It's always going to be, it's almost like, this one's kind of like a matched pairs example, or a one population sample mean with only a sample variance. We're using the student t-distribution. We'll have certain degrees of freedom. We can find critical values, compare the test statistic to the critical value. So we could also use that test statistic, which comes from a student t, so it's a t statistic. We could use it to find a p-value, compare the p-value to alpha. The steps are really the same. Okay? But we don't have to do as much of this by hand because when we do linear regression, you don't want to do it by hand. And I'll kind of give you a sneak peek as to why here in a second, but we don't want to have to do all this by hand. So we're going to have Excel do it for us. So I had this example where I had some data where I looked at the median income and 73 observations. Oh, sorry. I had 73,000 observations. I had income and the number of days that someone smoked marijuana or used marijuana each month. Right? Now, this was came from a younger crowd, also from oversampled from lower socioeconomic kind of status areas. So the income here is very low. I mean, some of the kids there's 14-year-old kids in this. So I mean, we're talking about kind of summer jobs and things like that. So, but still, it'd be interesting to look at what's the relationship between these two variables. And so what I kind of have this set up as, I can use Excel or another program called Stata. I'll show you both of those outputs from Stata and from Excel. So it would spit something out at you like this, where you've got your x variable here, and it tells you what your y variable was right here. So my y variable, or my left-hand side variable, was income. My right-hand side variable was the number of days that someone smoked marijuana each month. So, or used marijuana each month. So what I've really got here is, just so we can kind of get a nice visualization, my y variable is income. I know that that's equal to some intercept plus the slope times the number of days they use marijuana each month, right? Okay, so this is what I'm trying to estimate. And the interpretation of B, remember, it was the slope. So the interpretation is always a 1 unit increase in my x variable would predict that the y variable goes up or down by whatever that coefficient on B is, right? Whatever that estimate, right, that coefficient estimate for the relationship between x and y is. So we go back to the output. And here it's a little small. Hopefully it is showing up a little better than it looks like it is on my screen. But the value here, that coefficient estimate, is negative 253. So I found that looks like the relationship between income and the number of days someone smokes marijuana is negative. In fact, I can go one step further. If someone smokes marijuana one more day a month, I can expect their income is about $250 lower. Okay. Now, notice it gives me some other output here. It gives me a test statistic. It gives me a standard error. We'll talk about that in a second. And it also tells me the p-value. Right? And this is kind of for the p-value, treating it as like a two-tailed test, right? The default. So we have a p-value of 0 here. So not only can I say that that relationship exists, I can say that I can reject the null, which remember the null was that the relationship was equal to 0. So I can reject that with very high levels of confidence because that p-value is pretty much 0. Right? So it's going to be less than any alpha that we want to look at. The test statistic will be very easy, right? You're going to take whatever that coefficient estimate is on B. This assumed true coefficient value is always, we said 0, so that pretty much drops out. So to get your test statistic, you always just take your coefficient and you divide it by your standard error. So remember, in all of our other test statistics, we had the square root of the sample variance over the sample size, or the square root of the sample proportion times 1 minus. We had something in the denominator, but the denominator always represented the standard deviation of the statistic we were looking at. So the standard error is the standard deviation of the statistic we're looking at, which is this coefficient. Right? Now it's a little bit different than just a standard deviation. The standard error, you can kind of see what we're really doing is we're taking the actual y values in the data. We're going to subtract these predicted y values, which we'll talk about these in a second. I'm not going to make you do this. This is always going to be done behind the scenes, but this is, if you're more interested in, this is where the standard error is coming from. Okay. So, but really all you need to know is to calculate your test statistic. If you have the coefficient estimate, you have the standard error, divide the coefficient estimate by your standard error, and that will get your test statistic. Right? Same thing for the constant you could do here as well. Okay. So, how do we interpret that coefficient? I kind of talked about this, right? If it's negative 253, it's if the number of days you smoke marijuana goes up a month by 1, because this variable is measured by month. So if it goes up by 1 day, you expect that income of that person to be $253 lower. Right? So the standard is always a 1 unit increase in the x variable causes whatever that coefficient estimate for B is, change in your y variable. Decrease if it's negative, increase if it's positive. So what about A? What about this intercept? How do I interpret that? Well, A, right, would essentially be, this is the way and sometimes it will be kind of goofy depending on the variables that we're looking at. This one, the interpretation makes a little sense, right? Oh, I don't want to erase that. I actually needed that. So here's income. Here's A plus B times kind of the number of days they smoke marijuana, right? So the interpretation of A, if I can get this to focus, it looks a little bad here, is that if the number of days that someone smokes marijuana is 0, A would be the expected value of your y variable, right? Because if your x variable is equal to 0, this drops out, and the intercept would be what you would expect your y variable to be if your x variable is equal to 0. So the interpretation of my intercept is if the x variable I have is equal to 0, A is going to be the expected or predicted value for my y variable. Or here, if I smoke marijuana 0 days a month, I can expect that my income is whatever A is, and if we go back, that value was what, 32,000? So if someone smokes 0 marijuana 0 days a month, you can expect that their income is at what, $32,000. Okay? So we're now just going to have a general form of how we interpret both the intercept and the slope coefficient, or this coefficient estimate for the relationship between the x and y variable. Look at a couple more examples, and I'll show you how we can do this in Excel today a little bit as well. So I've got this kind of linear regression example now. What if I did birth weight and kind of whether or not the mother smoked? Well, sometimes we've got these variables that are binary or ones or zeros, right? Whether or not the mother smoked, right? Before, the number of days someone smoked marijuana, that could go from 0, 1, 2, 3, 4, 5, 6, up to 31, I guess. But this variable of whether or not the mother smokes is just a 1 if she did while pregnant and 0 if not. So now a 1 unit increase in my x variable would mean that if the mother goes from not smoking to smoking while pregnant, whatever our estimate for B is, that's how much the birth weight would we expect to be higher or lower if the mother smoked, right? Because a 1 unit increase is going from a 0 to a 1, not smoking to smoking. So here our coefficient estimate on that value B is -213. So if a mother smokes, goes from not smoking to smoking while pregnant, you would expect birth weights to be 213 grams lower. Okay? What's the test statistic? Well, I've got my coefficient, I've got my standard error. We said, how do I get my test statistic? Simply divide that coefficient by my standard error. So -213 divided by 48.9. Do I have it on here? No. It should be right around -4, right? So -4.36. If we actually divide -213 by 48, you'll get -4.36. And I'll kind of put the answer in when I'll post another version of the slides that has this circle. Okay. What's the interpretation of the intercept here for A, or the constant? Sometimes instead of intercept we call it constant. Well, it would be that if a mother doesn't smoke, right, if the x variable is equal to 0, that'd be if a mother doesn't smoke while pregnant, the expected value of birth weight would be A, or the expected value for a mother doesn't smoke is 3,427. Okay. All right. So we've got some more interpretation. So how are we getting these values for A and B, right? I've kind of showed you the results, but how are we actually getting them? What's going on behind the scenes? So I'm going to explain it. I'm going to go over it relatively quick because I'm not going to expect you to have a great understanding of exactly what's going on behind the scenes. I want to more focus on how do we interpret the results, because Excel is going to do everything behind the scenes for us. And we do have to have some understanding of what's going on. But it's more about how do we interpret the results that we get, because Excel will do all the heavy lifting and give us the results, and then really what I want you to be able to do is to be able to interpret those results. But we need to have a little bit of understanding of what's going on behind the scenes. So for any y variable we have, right, it's going to follow this relationship where there is an intercept and it does change as the x variable changes. But right, we know there's a lot of other things that go on, like for income, right? Yes, the number of days that someone smokes marijuana might impact income, but there's going to be a lot of other things that affect someone's income, right? So if I try to just predict income with a number of days someone uses marijuana, I'm going to be way off, right? Or I can think about if Y is income and X is the number of years of education. Well, if I try to predict Bill Gates's income based off of the number of years of education, I'm going to be way off, right? This error term epsilon is going to be huge. So we have the actual y variable, but all we can do is come up with this predicted y variable, what we'll call y hat, right? So once I have this coefficient estimate, for B and for the intercept A, I can plug in values for x and come up with a predicted y value, right? So let's say I go back here. If I wanted to say predict, what would the birth weight be for a mother? Actually, this one's better. I'll say, what would the expected income be for someone who smokes marijuana 5 days a month? Well, your value of the intercept is 32,449, and then you would subtract from that 253 times those 5 days, and that would give you your predicted income for that person, right? So we can come up with these predictions for y, or y hat, And notice the only difference between the actual y and the predicted y is this value, this error term. Right? So what can I visually think about this error term as? Well, here, let's say I have all this data. Right? I've got this scatter plot. Here's all my data. I plotted it all. I draw this line of best fit, or I use Excel to really come up with like kind of what this line of best fit is going to be. Excuse me, sorry. What if I have that line of best fit? Really, what I'm saying is, you tell me any value of x, I can plug it in to this equation where I have values for a and b. When I plug in that value of x, I can tell you the predicted value of y. Right? So let's say I think about, okay, this x value, I plug it into my line of best fit, it predicts that y would be about this high. Right? The actual data point I have that has an x variable, or sorry, an x value equal to that is way up here. So for this observation, my prediction would be off. So the difference between the actual y and that predicted y, that represents my error term. So for that specific observation, my line of best fit isn't going to perfectly predict what that y value was. So I'm going to have a kind of this error term. I kind of under-predicted it. So for this particular observation, they had a positive epsilon. I can think about for other ones, other x values or other observations here, well, I would predict the y value should be here, it's down here, so there the epsilon is negative. So for all these observations, I'm going to be making errors in both directions. Right? Some of them are kind of positive, some of them are negative. If I've got the line of best fit, right, what that line should be is that it has minimized all those errors. Right? If I drew a line like way up here, well now at every single x, I'm going to have huge errors, right? So what I'm trying to do is get to the line that best fits the data, because then when I add up all these errors, I'll have the lowest amount, kind of the smallest sum of those errors. Right? So what we're really trying to do is we're trying to minimize the sum of those errors, and then we're going to square them. So kind of squaring them does a couple things for us. So first of all, just like when we're calculating the variance, it treats errors on either side, positive or negative, kind of equally, right? They kind of, once they're squared, they're both positive values, so they're both adding the same amount to that kind of sum. But more importantly, squaring them over penalizes really bad errors, right? Because if my error, let's say I was off by 1, well, 1 squared is just 1, so only 1 gets added to that. But if I make an error of like 100, well, now 100 squared, right, is what? 10,000? 10,000? Yeah. So now I'm adding way more than 100. Like I'm adding 10,000 to it, right? So it over penalizes really bad errors. So we want to try to minimize this. Well, if we write out what the error term is, it's just the difference between the actual y value and the predicted y for every single observation, right? When the sum from I to n, I equals 1 to n, so it started the first observation, go to the very last observation in my sample. So for every observation, go through, find the difference between the actual y and the predicted y, squared. Well, I can write out my predicted y as well. It's just going to be whatever this value of a and b are, times, for that specific observation, how would I make the prediction? Well, I'd have to use the actual x value from that observation. Okay? So this is what I want to try to minimize, right? So I'll take a derivative in respect to a, set it equal to 0. Take a derivative in respect to b, set it equal to 0. I've got two equations. I've got two things that I'm trying to choose, or two unknowns. So two equations, two unknowns. I can actually solve that. I mean, it takes some time, it takes a little bit of algebra. But if we do solve it, right, we get something that looks like this, right? And there's kind of other forms of it that might be a little bit easier to deal with our calculator. I don't want you to worry too much about this. I might go through Excel tomorrow and kind of kind of show you how we could solve in Excel this way. But really, all this math, right, going through every observation, take the difference between that observation's x value and the average x value, multiply it by the difference from that observation's y value and the average y, add all those up, go through each x observation, subtract the average, square it, add those up. That's going to give you that slope coefficient, right? If I took that derivative in respect to those two variables, set them equal to 0, I had two equations, two unknowns. After I did the algebra, this is what I get, right? Now, I'm not going to make you do this by hand. We're very fortunate we don't have to do this anymore. We can have Excel do this for us, or other statistical programs. But we're primarily going to use Excel. Okay. So, if we were doing this by hand, we could do this, or we can just kind of use Excel, which is what we're going to do. All right, so we kind of skip past that for now. I said back to back to the earlier example. What I could do is figure all this out from that marijuana income example I gave you. The numbers would all play out and give me the exact same value. Like I said, I might kind of show you some of this tomorrow and focus on this a little bit more tomorrow, so I'm kind of skimming through it today. Okay, so we're going to do multiple regression tomorrow and maybe revisit this. But to end today, I did want to show you just a little bit of how we do linear regression in Excel. Okay? So I think in the slides, I've got, it might be the very end. Yeah, it's the very last slide. It kind of shows you how you add Excel onto your computer. Now, for those of you who have a Mac, it's a little bit different, and I'll try to kind of mention that as I go through the example that I'm talking about. So the very first thing that we're going to do is, the very first thing I'm going to do is zoom in a little bit. So we're going to go to File, and I believe at that point, instead of going to File, if you're on a Mac, you want to go to, you should have a bar at the top that's like Tools, right? So instead of going to File and then Options, like on a PC, you should just have like a Tools button up here on your toolbar. So once you hit Tools, you'll get something that looks similar to this. You want to click on Add-ins, and it won't look just like this on a Mac, but there should be something then that you see that says Add-ins. You then go down here to Manage Add-ins and hit Go. And I've already added it onto my computer, but usually it'll start out, this won't be checked. You want to hit the Analysis Toolpath, click OK. Now, under your Data tab, it should show you this Data Analysis option, but you have to go through that process and add in that Data Analysis kind of toolpath in order to use it. Right? So like I said, on a Mac, it should be Tools, and then you kind of can see the add-ins, and then you click on the Analysis Toolpath. Right? Actually, what is it Analysis Toolpath? I've already forgotten. Add-ins, yeah, Analysis Toolpath. Okay, right here. Okay. So once I have that in there, how can I start to get these estimated coefficients? Because I don't want to go through and try to calculate the sum of the squared errors. Yes, I have an equation for it, right? It's the difference for every value's x value, or every observation's x value minus the average x times its y value minus all this stuff. I don't want to do that though. I want to use this regression tool. It's on the Data Analysis tab, so I hit Data Analysis, Regression, okay. Well now, let's say I want to know what the relationship is between height and weight. So these should be blank, but I was probably doing something in Excel earlier. So if I want to find the relationship between height and weight, right? So I might think, okay, weight depends on height. My y variable would be the weight of someone, so I'm going to select that entire column. Hit that. The next one is the x variable. So a little trick here, if it sends you to the bottom, instead of scrolling all the way back up, if I kind of remember, oh yeah, this was my weight and here was the height was right next to it, you can actually select the very last observation, hit Control Shift or on a Mac, Command Shift, and hit the up arrow, and it'll select all the way back up to the top. So that's kind of a nice hint, so you have to do a bunch of scrolling, especially if you're on a laptop. Okay. Now, one thing that's important here is I want to make sure that I say I selected the labels. If I don't, it's going to give me this error because it's got non-numeric data, right? So it doesn't like that. So I make sure, oh yeah, I selected the labels, right? And that's nice because if I don't, I'll show you in a second what happens if I don't select the labels. So I select the labels, we're good, hit OK. On another sheet, it'll put my regression analysis. So we're not going to talk about anything up here yet, other than it gives us our observations. So we've got 7,160 observations. It gives me my coefficients for the intercept and for that variable of height. It's got the standard error, test statistics, p-values. So with height, how can I interpret this? Well, if I'm writing this out, well, might be able to easier to just kind of write this out in Excel since I've got this pulled up. So zoom this in, we'll go to 200. So how would I kind of interpret this? And oh, come on. There we go. So what I just did was I had weight as my y variable equal to a plus b times height. So the way I interpret this coefficient b on height is if someone gets 1 inch taller, right? 1 unit, 1 inch taller, I would expect that person's weight to go up by 4.7 pounds on average, right? That's another important thing about these coefficient estimates. They're always, this is the effect, like the average effect. For some people, getting an inch taller, maybe it adds 5 pounds, but for some, it only adds 4, right? But on average, it adds 4.7, okay? And it's pretty significant, right? A p-value is 0, so we could say that we can reject the null at the 90, 95, and 99% confidence levels. Okay, so that's kind of our interpretation. And here's a good example where the intercept is a really weird interpretation. So remember, it's if the x variable is equal to 0. So if someone is 0 inches tall, the expected weight would be negative 128. Now I know that's like sometimes the interpreted intercept isn't even a real possibility, right? And I can give you a slight kind of idea why that is, and it's okay. That's still how we interpret it. It's because, like, how can someone have negative weight, right? That doesn't make any sense. But if you think about what we're doing, I'm going to make sure I draw this. There we go. If you think about what we're doing, like maybe we have data that's over here, right? I mean, and the problem is we could never see data, even if we were looking at infants, right? We would never see data where someone is below, like, I don't know how small infants get, but like 20 inches? I'm sure we have premium, but let's just use adults, right? We're not going to see people that are anything lower than even a couple feet, right? Even if we're looking at someone who's really short, we're not going to see someone who's only 5 inches tall, right? So we have all this data, and we have height on the x and weight as our y. So when we do the line of best fit, well, yeah, we don't ever see anyone who truly is like 0, like height is never 0. And that's why we get an intercept that's negative, right? Because we don't see anyone at heights below this, right? And so that's still how we interpret the intercept, but sometimes the interpretation will just be weird because it's just things that we can't see happen, right? And it doesn't matter because we're never going to have to make predictions for those values anyways, right? All right. Okay. So, oh, the one other thing I wanted to show you, why is selecting the labels important? So if I go to my data analysis tab again, hit regression. So let's say now I only select, I don't select that label of weight, I just select the actual values and not the words of weight and height, right? I then say, okay, I didn't select the labels. Now if I hit OK, it still puts this regression output here, but notice it just tells me it's an x variable. Well, okay, but what was the x variable, right? And this isn't as important. I can remember here, like, oh yeah, I used I used height as my x variable. So it doesn't seem as important now when we only have one variable. But tomorrow what we're going to talk about is we can actually add several variables to that right-hand side. Okay. So tomorrow what we'll go through is what we're going to call multiple regression. Where did I stop? Here we go. So we'll talk through some stuff about multiple regression tomorrow. I'll show you how to do some more work in Excel. So I'm not going to have as many standalone kind of Excel files for the rest of the semester. Matched pairs like the Excel was contained in the lecture. Today, basic linear regression contained in the lecture. And then tomorrow, for multiple regression, the Excel will be contained in the lecture on multiple regression as well. So no separate Excel videos anymore. So that's it for today. We'll pick up and kind of work on multiple regression tomorrow. And another thing I wanted to mention was I would have, hopefully moving forward, I made that extra credit assignment available for getting points back on the midterm, and I was kind of shocked that there was people that actually didn't do it. It was worth 15 points. I think the average of someone who actually turned it in was like above 13 points. Also, some people that turned it in didn't even complete it, and so if you turn it in, more likely than not, you get at least 13 points added to your score, which is more than a letter grade, right? And so people could have bumped their grades up from F's to D's, D's to C's, and I saw a lot of people kind of not do that. If I make anything like that available throughout the semester, I highly suggest doing it. But you don't really have an excuse now. I'm trying to make give that and make that available. So please continue. Do your homework assignments. If I offer a little bit of extra credit, I highly suggest kind of doing that because we still have one exam to go. it will be a little bit tough. We have currently the Connect and an Excel assignment that are due in about 2 weeks, or due 2 weeks from last Friday. Apologize for the dogs; they're having a tough day. So, all right, I will see you tomorrow at 10:30.